What up, athletes? Whoop, whoop. All right, let's do this. Let me get some stuff out of the way. We are going to talk about proving segment relationships. And you know what your learning target is today? It is, I will prove theorems about line segments. I will prove theorems about line segments. There we go. Your warm-up today, it says give the correct order for the set of statements. I just want you to go ahead and write them out in the correct order. And it will end up becoming a paragraph proof. So take a minute, pause it, ready, set, go. All right, I'm assuming you paused it, worked on it. Here we go. Here's how it works. It should end up, let n plus 1 replace any two consecutive integers. So that was number what? Let n plus 1, that was number 2. And then it says n plus 1 equals 2n plus 1. So that's 4. And then because 2 times a number is always even, adding 1 makes it odd. So 2n plus 1 is odd, which is number 3. Oh, wait, excuse me. No, that's number 1. And then the last one, because 2n plus 1 is odd, the sum of any two consecutive integers is an odd number. That's 3. And there we go. We have our nice little paragraph proof kind of done out for us. So, there we go. Good job. All right. Now we are going to get on to proofs about line segments. So, what does it say here? It says QT is congruent to RV. So that means this distance, QT, is congruent to this distance, RV. And how does it start out? It starts out saying that QT is congruent to RV. Let's go ahead and zoom in there a little easier to see. And that's a given. And what did I tell you? Whenever we say something's congruent, guys, 99% of the time, it's going to follow up with it equals it. So QT equals RV, right? Okay? That's the definition of congruence. Now watch what happens here. It says QR plus RT. So that says QR plus RT is equal to RT or QT, right? So QR plus RT is equal to QT. And what that comes off of, if you look on your list, we've got some new postulates right here, which I go over in another video. We have segment addition postulate, which says if A, B, C are collinear, then point B is between A and C, if and only if AB plus BC equals AC. So what does that tell me? It tells me if I have a line segment with 3 collinear points, then if I add up the small parts, they're equal to the whole. And it's if and only if, which means it works forward and backwards. So we can say if AB plus BC equals AC, then point B is between that, right? It's very similar to the betweenness from earlier, the definition of betweenness. It actually comes from that. This is for line segments. So we're going to use that because what we're doing here is we're just saying, hey, if I add together QR plus RT, it's equal to the whole thing. And I'm also saying in the same breath, RT plus TV is equal to all of RV. And that's just our segment addition postulate. 3 little abbreviated words there, right? Okay. And now that I know that I have segment addition, let's look and see what we have left here. We really just have a reason, and we have a definition. I know we have 3 different blanks here, but we're going to have to use one of these twice, and we'll figure out which one it is. It's either going to be substitution property or it's going to be segment addition postulate. We'll have to wait and see. We only have one actual given, so this is just a little problem solving to help you with it. But what we can say next is we can say QR plus RT. So that's this QR plus RT is equal then, because listen, Since we already said the whole is equal to the whole, now we can say the sum of the parts are equal to the whole. So we're doing a little substitution here. So since I know QT equals RV, I can now say the addition of the parts are equal to each other as well. So that's QR plus RT is equal to RT plus TV. And that, again, I said it as I was explaining it, that's substitution. Okay? Substitution. Now, we have QR plus RT minus RT equals RT plus TV minus RT. Notice we're subtracting RT from both sides. That is the subtraction property of equality. And so once we subtract that RT from both sides, boom, that's gone. That's gone. What are we left with? We're left with QR equals TV. Again, whenever you do that subtraction, that's called substitution. So substitution is the one that we're doing twice here. And then, what did I tell you? It works forward and backwards. As soon as we say that something's congruent, we're probably going to say it's equal. And as soon as we again state something's equal, we can then state it's congruent. And how can we do that? Definition of congruence. Boom! Look at that. Good stuff right there. All right. Now let's go down here. Let's look at this one. Got a nice little proof going on right here. We have that GH is congruent to FE, right? So that's GH is congruent to FE. And we have that HD is congruent to DE. So HD is congruent to DE. And we want to prove that the whole of GD is congruent to FD. Okay? So we have our given. GH is congruent to FE, and HD is congruent to ED. That's our given. You can put both givens at one time. And then immediately, what are we going to do? We're going to say they're equal. That's definition of congruence. This one doesn't have choices. We've got to come up with it. And then I'm going to say, all right, GH plus HD equals FE plus ED. And that is the addition property of equality. So we just said GH plus HD equals FE plus ED, right? Okay. Now we're going to say GD equals GH plus HD. So if GD equals GH plus HD and FD equals FE plus ED, that's very similar to what we have up here. Which, what did we use? It's called segment addition. Remember, we're saying the whole is equal to the sum of the parts, so that's segment addition postulate. We're just getting practice using it. And then the next thing we say is, all right, we know that GD equals FE. So GD equals FE. How do we know that? Well, we already said these are equal, so I said these are equal. Now I'm telling you, this is the same thing as saying GH plus HD, and FD is the same thing as saying FE plus ED. So I'm going to substitute them in. So this is substitution. Substitution is kind of your thing. You're going to use it a lot. And then once we say they're equal, we can now say that they're congruent. Definition of congruence. That's the one we use all the time. Boom. 2 good proofs right there. Let's keep this on a roll. R is the midpoint of QS. If R is the midpoint of QS, then we know that those are the same. T is the midpoint of VS. Okay, we want to prove that QR is equal to VT. Now I'm going to write these as 2 because we haven't proven that. Or no, oh no, we're saying QR is equal to VT. Oh, my bad. That was part of the given. So because QR is equal to VT, I can say these are all the same length, right? And what we now need to prove is that RS right here is congruent to TS, which we can see that, but we got to prove it, okay? RT is the midpoint of QS, T is the midpoint of VS, that's all given. That's great, okay? Now we need to say, all right, QR is congruent to RS, and VT is congruent to TS. We know that because of the midpoint theorem. That's the whole point. The midpoint cuts it in half. So the midpoint theorem. All right? And then we have QR is congruent to VT, given. We have QR is congruent to TS. How can we do that? Well, check it out. If we have that QR equals RS, and we have VT equals TS, then we can substitute in for VT up here, right? Since VT equals TS, we can substitute that in and say QR equals 2S, and that is going to be the transitive property, because look at it. Let's do it backwards. QR equals VT, VT equals TS. We can cut out that middleman, right, and say QR equals TS, and that's going to be the transitive property. Okay, and then we have the symmetric property of congruence, which we can now say, all right, hey, isn't it also true? Let's flip this around. We can also say RS, segment RS is congruent to segment QR. And now look at what we've created. We've created another transitive property situation where we can cut out the middleman and say segment RS is congruent to segment TS. And this is one of those rare times where we had lots of congruency, but we didn't say equals at all. What? No definition of congruence happening here? It's crazy. This one's harder to follow simply because you got to really kind of follow the pathway going on here. All right, still a good one. And then last but certainly not least, let's go ahead and look at this one. It says CD is congruent to DE. So CD is congruent to DE. AB is congruent to BC. I'm going to hold off on this one because I want to say AB is congruent to DE. So AB is congruent to DE. But then let's go back here. AB is also congruent to BC, which means each one of these parts are congruent to each other. But we really want to prove that BC is congruent to CD. And there's going to be some transitive property happening here. So we'll get to that. Well, let's go ahead and look what we have. We have our given, right? And now we're going to say, all right, BC is congruent to AB. Well, how do I know that? I know that because the symmetric property. Because all I did, guys, is what? I just flipped this around. We have the given that AB equals BC. We're just flipping it around. It's going to help us do the transitive here in just a second. And then you'll notice, what do we have over here? Really the only statement available, right? So we have BC is congruent to DE. So segment BC is congruent to segment DE. And how can I say that? BC is congruent. So I have BC is congruent to AB. And we have that BC, or AB, is congruent to DE. So if BC is congruent to AB and AB is congruent to DE, right? Look at that, look at that. Boom. We follow that pathway, we cut out the middleman, and we say BC is congruent to DE, and that is the transitive property, which we see as another one of our choices here, which I haven't crossed these out because I got to use one of these twice, and we'll see which one it is. So now I know BC is congruent to DE. Okay. Then we are also given CD is congruent to DE. And we're going to flip it around, right, to help us with the pathway. And we're going to say DE is congruent to CD, and that's just the symmetric property again, right? Because I need it in order, because now that I have DE is congruent to CD, let's go back up here. I'm going to change out the BC for CD, because up here we have BC equals DE, right? So if BC equals DE and DE equals CD, I can take this and do another transitive. I can swap those out, and I have BC is congruent to CD, which is through the transitive property, and we wanted to do that so that we could get our proven statement, which is BC is congruent to CD. So now we are done. This is proven. It's a little mind-bending sometimes, guys. This takes me a minute to look at it. You notice I was stuttering there going, because I've got to see the pathway. We're going to work through these. It's going to be awesome. Good job, guys. With that said, peace out.